It looks like I'm tied up now. I once went to a course in teaching. It may not sound like that, but I actually took a course in pedagogic. And then the teacher said that there is two types of lecturers: those who walk all the way when they lecture, and those who sleep. And now I think I was among those who were walking all the time. So now I've been tied in. I cannot walk any longer. So we'll see how that goes. But as you all know, PGP has a master program and a PhD program. And in the master program there are two basic courses. This is PhysGeo 4200, that's a case study. And then there is the PhysGeo 4300, that's the methodology. These are integrated courses, and they are also used by the PhD students, then under the 93 and 92 respectively. Of course, this thing with the PGP master is quite an experiment. It's a unique experiment because we are trying to put geologists and physicists in the same class. And I guess it's not only unique in Norway, but it's probably also unique on a world basis. It is a very work-intensive course with extensive report writing. And I think also we are trying to make it so that it is as close as we come to this popular term, research-based teaching. And the intention by this, I wasn't part of creating it, but I guess the intention was to create a new brand of master students, what we could call geophysicists as opposed to geochemists. And of course it was also then meant that these students should be very attractive at the working market. And I also assume that because we are a research institution, that it was also the intention to train researchers. And more than that, I think also we thought that this course should be create research. Maybe it was meant that the case study should be a dynamo for creating research activity on PGP. And of course it is interdisciplinary. It had to be interdisciplinary. No, I have been part of this case study for quite a few years, and I thought now as PGP was approaching an end, it would be nice to give a summary of this and see what have we achieved up towards the intention. So what I will do, I will give a short introduction to the working schedule in our courses, and then I will report a little bit on the dynamics in the mixed geology physics groups, and then I will focus on what we have obtained in terms of research. When we put a lot of energy into a course like this, we see here we are flying helicopters, and from that we swirl up a lot of dust, and from this dust maybe also there is new research avenues that emerge. I will also come into that. And then at the end I will try to view the result of this course in light of the intention we had. Of course, for every year we have had a kind of a topic and a field area. And of course, to find the right topic and the field area, we need firstly to find the problem that is in the intersection between physics and geology. And of course, we also want to have a topic at the research front. And I've also been trying to find topics that is related to upcoming research at PGP. Because if we start something that's after PGP has done the research, then it's too late. We have to be in the front. Of course, to do this, we need to have some pre-knowledge of the area. And we have limited amount of money, so we need to have a low-cost logistic like here, where we are picking the dinner at the ferry quay. And we can see now how the French really knows where to find the small good things, and the Italian is more skeptical, and the Norwegian doesn't know exactly where to go in this. The topics of the recent years has been like this. In 2008 we had ocean floor processes, and we went to Leka and Feragen. In 2009 we had the topic reaction between CO2 and ultramafic rocks, also to Feragen. Of course, this was just in the front when Anders started his projects on CO2 sequestration. In 2009, we had the title like CO2 sequestration in sedimentary basins, and because quite a lot of physicists are now working on how to sequester CO2 in sedimentary basin, it's a little bit important that they know how the architecture of a sedimentary basin is, and therefore we went to Solund. This year the title was Friction and Earthquakes, and we visited Holsnøy in the Bergen Isles. The course starts with a week of fieldwork, and this shows where we have been operating at Leka-Feragen, Solund and Bergen, and we also see a group, this year's group of interested students that is working hard with their mapping. And they have done a good job. This is the map from this year, where they have been mapping out faults, and we can see here how they have been able to show the displacement on the faults, and we see how they have where they are collected or drilled their samples, and also they have then made details of how the rock is sheared and get into the eclogites. And I must say that I've been very impressed by how this has worked with the students, and particularly when you put physics students out into the field. They have handled this very well, and you can see also they are very good with the drilling equipment when we collect the samples. I also find it nice that they really document how they collect the samples, like here where we see where they show how they cut the drill core, how they put the thin section, and the picture of the drill core with the scale, everything as we like to see it. And I wish I had done the same thing when I collected my samples. From the sampling and the mapping, we take the material to the labs, and we use the microscope, the optical microscope, and you can see here we can already focus in on the fault planes and see how we displace this thing, and then we can go even further. We can take a grain like this, go to the optical microscope. This is a scan from the scanner in Jasmin's room, and then we can take this onto the SEM and electron microprobe, and really get a detailed view into how the fault operates and what happens with the minerals when the faulting occurs. So then, because this year is not yet finished, the students are still working, so I thought instead of dwelling with that, I would rather try to see what we have done on Feragen, because we went there twice, and the reason why we went there is clear from these images here. Firstly, we see the fracture system, which is clearly a problem that we can deal with both from geology and from physics. And another thing we saw was the carbonation of the ultramafic. Like here, where we see all the carbonates and the fractured serpentinites. Another problem that is very, very in focus today: how we can sequester CO2 in peridotites. And just to say a little bit about the Røragen, this is an ultramafic body. That means that it is a rock composed of dominantly olivine, and it is in contact with abundant serpentinite, and it is overlain by a conglomerate, serpentine conglomerate. And we notice another thing, that there is a lot of symbols here, and these symbols represent chromite mines. This area has been mined for chromite over a number of years, up to 1930. So there is the basis then for what we were interested in, both how is the alteration of this rock going with respect to serpentinization, and also can we learn about carbonatization of ultramafic rocks from what we see at Røragen. And one thing we have been doing is to map out the fracture zones. This picture here is a little bit, you don't know what these crops here are doing, but it is actually a scale for the helicopter. So when the helicopter was hovering over here and Dag was taking photographs, there was a few hunters working in the area, and they realized that there was something funny going on, so they thought there was some bad accidents up here, and when they saw all these crops lying around. But the purpose of this was to map out the fracture zones, and then this has been used then for fracture analysis in fish geo in a couple of years. It was quite a tough period up there because it was bitterly cold, but you can still see that the students are at least trying to smile. A little bit about the importance of serpentinization. Firstly, when we react olivine to serpentine, it's an important mineral reaction, and it influences the petrophysics. So it has implication for the how we image the lithosphere with geophysics. It has implication for the density, the rheology, and the magnetic properties of the rock. It is also so that you can produce methane from during this process, and as I said, we can also sequester CO2 in ultramafics. I must say that although we have put quite a bit of effort into this, we are still not finished with this, and at the moment there is a lot of activity going on here at PGP to find out more about the serpentinization, the mechanism behind the reaction, and how does the rock crack and how is fluid introduced. But we have also reached important things. For example, when Andreas went into the mines, he found that the wall was coated with carbonates. And because we know that these mines operated till 1930, we know that these carbonates here must be almost present day. So there is a present day carbonatization. So this is then a basis for a paper that Andreas is writing, with a title like Ongoing Carbonatization of Peridotite. And from the work he has been doing, here is a backscatter image of these same carbonates, and we can see that not only do we form a lot of carbonates here that is growing, but we also seem to crack the rock during the carbonatization. So this paper is, I guess, soon ready to be submitted, and it has the highlights of ongoing carbonatization. And he has also discovered that the pH in the water in that area is very high, almost up to 10. The fragmentation I already mentioned, and he has also done the stable isotope work to show that these are almost surface processes that goes on. But how do we get this high pH? This is probably required to carbonate the rock, and this is then the basis for another paper by Jørn. It is on brucite dissolution and carbonatization. We can see here how the brucite, this gray phase here in the serpentine, is along the veins replaced by a secondary mineral, pyroaurite. It's also a carbonate, hydrous carbonate. So we can see how the brucite dissolves and how we form these new phases, and this must kind of relate to weathering. Jørn has then investigated this with AFM and also with Raman. it's necessary when you look at these secondary minerals that you form during weathering to use Raman, because we cannot really find out directly from the electron microprobe. And this is just two of the spectra from the Raman, which has been used to both to identify the pyroaurite and also the brucite. So that's another paper, and then a third paper that is under development is the thing that bases on these white veins we can see here. This is a field image showing us the metadernite, and then it's in contact with the metaharspegite. These are difficult names, but I think the physicists have learned these names now, at least those who have gone through the courses. But the thing is that we can use this vein here to address the process of serpentinization and a little bit more about the kinetics of the reaction that happens. Because if we look into that, we can see firstly that these fractures, they stop at the contact of the peridotite. They are only found in the metaharspegite. And when we blow up this with a backscatter image, we can see that there is a thing here that implies rapid reactions and maybe also crack seal things in relation to earthquakes. So from this, Oliver has concluded that this is a far from equilibrium reaction in a gel-filled fracture. And there is more nice images here showing how the fractures are filled with this andradite garnet. And then, since andradite requires calcium, we can also say something about where is the calcium source, and we can therefore trace kind of the mobility on how far the element has traveled in this system. And by analogy to spherolytic growth, we can use this to say that this was probably a highly non-equilibrium condition. But I'm sure we will hear more about that from Oliver. Another thing we hope to do is a more general paper on weathering or carbonatization of peridotite in a subarctic climate zone, and then deal both with the mechanical, chemical, and mineralogical aspects. And we hope that at least Ivar will help us with the mechanical part of it, so that we can make a paper of that. The basis for this paper is a kind of an extension of Andreas's paper, because when we see the weathering like this, the rock breaks apart in blocks. Then, of course, the condition that we get under one of these blocks here is pretty similar to the thing we find in the mine openings. And this is also what we see when we lift off this block. We see that the rock is coated with white stuff, which is carbonates. Whether these carbonates is also forcing the thing apart still remains to be solved. Oliver has also has sliced this weathered peridotites. Unfortunately, light is a little bit. If you turn off that a second. Now still it is dark, but we can see that this glass have a nice weathering wind, and we see more than that. We see that the weathering penetrates into the rock, and sometimes we get more like a random walk alteration of the peridotite. And from modeling, we are hoping that we can get some more information on how this is going. Is the weathering just following the serpentinization veins, or is there also a dynamics in it in forms of cracking? What we know now from the work we have done is that these zones in the weathered clast are filled with hydromagnesite, and some places they are even filled with this pyroaurite. So these are the weathering products, and the question is if this bending of that means that it has a force of crystallization that cracks the rock open. So that is the topic for this hopefully coming fourth paper from the area. So I said that when we put a lot of effort into an area, there is also a lot of dust being stirred up, and a lot of new things can also come. And I'm just going to point to a few things that we have found that could also be very interesting topics for research. Firstly, we see that the olivine, when it's altered to serpentine, is fringed, and then it is surrounded by a bright rim. It happens that this rim is a nickel-iron alloy, and this seems to define the margin of the ring. Now we can find out that this nickel must come from the serpentinization process, since we know that we can measure the nickel concentration here, and we can measure it here, and we find out that here it's low, here it's high, and therefore we must have kind of a transport of nickel to this rim. That also tells us something about the serpentinization process. But more interesting is that this also brings in what we call the Fischer-Tropsch synthesis. Fischer-Tropsch means that you can produce hydrocarbons abiogenic. You can produce it through the serpentinization process. And actually in the chemistry department there is a group working exactly on this, how they use this nickel alloy as a catalyzer for cracking oil. And I guess, although we have not done anything on this so far, it's certainly also a very nice research avenue that we could continue along. Yeah, this also shows us this cell structure of the olivine with the nickel alloy sitting on the rim. Of course, this also brings up another thing, that is, of course, the original life. How because many things that also the life originated like in a serpentinite like this, and maybe there is something there also that could be developed. Another thing that we have come across is something we could call the geochemical cycle of chromium. I already said that ultramafic rocks are the main source of chromium, and that's why we have all the mines at Røragen. And those are found mainly in chromite with a formula like this. I hope I have. Maybe I missed out the two there. The chromite has in the Feragen has the form like this. There is actually a lot of work being carried out on chromite, because chromite is a poisonous stuff, not when it is in the trivalent form, but when it's oxidized to the 6-valent, then it becomes poisonous. And for example, in California, a lot of the soils over these peridotite are not nice stuff, and there is a lot of remediation going on to try to prevent the oxidation of trivalent to 6-valent chromium. This oxidation is mainly taking place when we reduce manganese from, for example, Mn4 to Mn2. Then we can, and that is actually the only element that can oxidize the chromium at an intermediate pH. And we know that this process is accelerated by a biogenic formation of Mn oxides. So can we then do something about this on Røragen? And the answer to this is yes. There is another important thing with this. If we look at the composition of the continental crust, then the continental crust is too high in chrome and nickel. If we compare it with an andesite. And this is not totally understood why it is so. People think it is because something happened in the Archean, but it could also be that if you had a little bit of weathering of the peridotite, maybe you could produce it in that way. Therefore, this is also a very rich research avenue that we could develop. I will just show you a little bit of what we find when we start looking into this, trying to follow the geochemical cycle of chromium, because when we weather stuff, then it's a question: where is the chromium going? And we were looking for this red clast up in the area, because we know from earlier work that these red clasts are really weathered peridotite. And when you search, you find. So we went up and found this red clast in the conglomerates above the peridotite. When we looked into that, we cut the samples in parts and found that they were carbonated and weathered, and as I said, they were derived from the peridotite. And when we started to look at the oxide or the chromite, it appeared like this. From the nice clean chromite we had in the peridotite, we find something that is quite complex, very complex. So this is a backscatter image of this chromite, and we can look into these fronts where they are altering. And then we find this very funny structure like this. This is now our chromite, the original chromite, and then it is replaced in a pattern like this. It must have some fingering structures, because we can see inside the chromite we find circular, actually not only circular, but they are also kind of twisted and indicating that there must be some tubular things going into the chromite there. At the moment we don't know how this forms, and is there an oxidation process that makes this nest form, or could it even be that it is bacterial things that are doing it? If we give this to people that works with bacteria, they would conclude that it is bacteria. I'm not ready to say that this has anything to do with bacteria, but it is the process by which the chromite goes in solution. Because when we map this, we make a chemical map across this, then we can at least see what happens geochemically. This is again our chromite grain, and we can see when it's altered, the alumina disappears. So this is still the alumina-rich chromite, but then this is low in alumina. The same thing happened with magnesium. Magnesium is kind of lost, and the magnesium and the alumina is both going into these cracks where we find the chlorite. And of course also some of the chromium is going to the chlorite. So we see a clear alteration of the chromite, and the nice thing is that we see that what is replacing the alumina and magnesium is actually manganese. So of course now this is very tentative, but this is exactly what one should expect from what is written in literature, that the manganese can oxidize the chromium, and then it could leave the system. In this case, not so much has left, but if there is other grains in the same area where almost all the chrome has gone, we can only see small patches of chrome together with manganese, and the rest is gone. In this case, we also have carbonated the rock, and this is a manganese-rich carbonate. So I think this is quite an interesting, also a very interesting research avenue to be followed up. So then I tried to convince you that this field course has been very quite successful with respect to creating research and even bringing up new research topics. So in that way, we can say that this has fulfilled our intention. And it's also my impression that the students work very well together and with a very steep learning curve. It takes quite a lot for the physicists to learn all these names that we are using all the time, but it has been very interesting to take part in this. When it then comes to the other intention with the course, it is also so that the research is carried out by the PhD students. I don't know, of course the master students only have 1 year to do research on, but it is also so that only one master student has so far continued in a project related to the case study. So I don't know if this is because the PhD student dominated so that the master student doesn't find a room, or it is because they don't have time to it. It may improve this year because now there is at least a couple of the master students that want to continue with the master thesis in relation to pseudotachelites and earthquakes. So maybe there is a change. When it comes to the interdisciplinary role, it's clear that we put them together and they have to work together when they are in the master course. But when we look at it afterwards, it's a question whether they stay together or whether they depart. And so far I think that that is my impression, that they kind of depart. So the question is if we are trying to create something that is artificial and not worth continuing, or whether this is something for the future. I don't have to decide this, but I made this presentation because those who are going to continue PGP or continue this avenue has to take a decision on this. How would we carry this on? Would we change it, or has it been a success? This is in many respects also the success of PGP. I guess we would like to see this interdisciplinary approach, and I guess we hope that would happen. I'm not sure it has happened. Okay. So that's all. Since I know that Trond has a hangover today, I thought I should keep. But so I don't take any question, but I would like to have some comments on what we think about the case study and its future. Thank you.